All right, so in the previous lecture I showed you which kind of discretizations for the time derivative you can choose for parabolic problems. Now, I would like to look at the hyperbolic equations, let's say in particular at the second order hyperbolic equations such as the wave equation. And I would like to investigate essentially along the same line as before, what that implies for explicit time-stepping methods and for implicit time-stepping methods, and which ones of these might be suitable for equations like the wave equation or similar equations with similar properties. So this is about the second-order hyperbolic systems or equations, and let me remind you the prototypical hyperbolic equation of second order is the wave equation. So the wave equation has two time derivatives of our solution variables minus the Laplacian, so two spatial derivatives equals f. Then it has initial values for the actual value and for the time derivative of the solution, and we have boundary conditions. And as before, the boundary conditions don't play that much of a role here. So the character of these equations is that of transport, where for parabolic equations, for the heat equation, you had something that smoothes out. For the wave equation, you don't have that. For the wave equation, you throw your rock into the water and produces a wave, and this wave is going to travel on in exactly the shape, maybe in smaller magnitude, but in exactly the shape forever. So that means that sharp features are transported along as sharp features, and there is no smoothing. And I will come back to this. This has one particular important aspect later on when we investigate what that means for accuracy, how big we can actually choose a time step. So we argued that for the heat equation, because the solution becomes smoother and smoother and essentially changes less and less, that we should be able to make the time step larger and larger. For hyperbolic problems, we can't expect this, because if you just translate, let's say, a wave that moves from x equals 1 to x equals 2, then you have to have a time step that matches this transportation speed. Now, if you go 100 units into the future, you have the same wave that is transported from x equals 100 to x equals 101, for example. So you have the same kind of feature at a future time that happens in exactly the same delta t, right, from 100 to 101, for example. And you have to expect that you have to choose the same time step at time t equals 100 as you chose for t equals 0. So let's say just from the character of these sort of equations, you cannot expect that you should be able to choose a time step that becomes bigger and bigger. And that is one of the things that is fundamentally different from the parabolic equations, where we expected that this can happen, or that we should be able to do this. So let us look at the wave equation, and I want to do the same thing as before. I want to look at the method of lines, because it is easier to analyze here. And if I do this, so that means I first discretize in space, I convert it into an ODE, into an ordinary differential equation, and what I get is that I get the mass matrix times the second time derivatives of my expansion coefficients at time t, plus the Laplace matrix times u equals the right-hand side. And here are the two simplest time discretizations. So if I choose an explicit time discretization, then I need to evaluate this term a times u at time n minus 1, and the same thing for the right-hand side. Whereas if I chose an implicit time discretization, I would evaluate it at time un. That's the time that I want to solve for right now, minus, and on the right-hand side, f also at time tn. The second derivatives here, I discretize this by the second order finite difference in time. Okay, so that gives me un minus 2 un minus 1 plus un minus 2 divided by delta t squared. You can get this by taking the time derivative of the time derivative and just using a central difference quotient for these. So that's the same for the explicit and for the implicit method. The difference lies here, un minus 1 for the explicit, un for the implicit method. As before, I'd like to consider the case where the right-hand side is 0. It doesn't make any difference for the actual analysis. It just becomes a little bit easier to understand what stability means. So if I choose an explicit method where the right-hand side is 0, then I can solve for un minus 1. So that's the only thing that I want to keep on the left. Everything else I want to bring over to the right. Then I can show that un equals 2un minus 1 minus un minus 2 minus delta t squared m to the minus 1a un minus 1. Okay, so everything on the right-hand side is computable because I already know what happened at times n minus 1 and n minus 2, and I can immediately compute the solution un at time tn. Okay. All I need to do is I need to multiply with m to the minus 1, and we can make the same kind of argument as in the last lecture, that basically m is something like a diagonal matrix that has entries of size h to the d on the diagonal. So it's an explicit method because I can write down un equals something that is immediately evaluatable. I don't need to solve a linear system for this. So to this sort of representation, I would now like to apply the same technique that we talked about in the previous lecture, namely the expansion into eigenvalues and eigenvectors of the Laplace matrix. Okay, so I have this sort of equation here, this sort of recursion to compute un from un minus 1 and un minus 2. And if I expand my solution again in terms of expansion coefficients mu k at times n, and eigenvalue is lambda k, and I replace again m by something like h to the d times the identity matrix, what I find is that I can express the expansion coefficient mu k at times n in terms of the expansion coefficient mu k at times n minus 1 and n minus 2 by this sort of relationship here. Okay, so let me look at this in some more detail. Let us assume that we want to define stability in the following way, namely that the, let's say, expansion coefficient here should be less than the bigger of these two. Or let's say, for simplicity, assume that they're about the same size. Okay, then I would get 2 times this one minus 1 times the previous expansion coefficient. And so an informal way of stating that something is stable is if this factor minus 1 is by magnitude less than 1, because then these coefficients cannot grow. And I can make this more formal, but I want to give you the essential idea here. So what that implies is that if I look at this again, that if this term must be less than 1, and if I plug in what I know about the eigenvalues of this matrix A, namely that they're h to the d times k squared pi squared, where k cannot be bigger than 1 over h, then I can show that this inequality here is satisfied if I choose delta t less than or equal 2 times h over pi. Okay, so that now turns out to be an entirely reasonable restriction. You remember that for the parabolic equation, the condition I had was that the time step must be less than or equal than some constant times h squared, and that meant that if I refine the mesh by once, so I make h smaller by a factor of 2, that I had to choose delta t smaller by a factor of 4. And that we consider as unreasonable. But here, if I make h smaller by a factor of 2, so I make the mesh finer by 1 refinement, then I need to take a time step that is also half the size. And that seems certainly reasonable, that if I get a higher accuracy out of the spatial mesh, that I should also expect that I should take a smaller time step to get the higher accuracy in time as well. So for them to be proportional, that seems reasonable. I can make a very similar argument for all explicit methods applied to the wave equation or hyperbolic problems of second order, where I will always come out with an inequality of the kind that delta t, our time step size, is less than or equal some constant times the mesh size h. What exactly this constant is depends on the method. So for the method that I have chosen here, I get something like 2 over pi. For other methods, I might get something that is smaller. So typically, the higher you choose the order of your time discretization, so if you choose, let's say, a BDF2, BDF3, BDF4, or a Runge-Kutta 4, you get something where you have to choose the time step smaller. So the coefficient may not be 2 over pi, which is roughly 0.6, but you might have to choose it, let's say, 0.1 times h. But by and large, the idea remains the same, namely that delta t is proportional to h. And that's quite reasonable. I would like to show you this in a slightly different form. So the actual wave equation, physically correct, has a term in here in front of the Laplacian that is c squared, where c is something like the wave speed. So if you want this wave equation to describe, for example, the propagation of sound or the propagation of a wave along a string, then typically what you have is that the c is a wave speed and it's squared. And if you go through exactly the same kind of analysis, what you find is that this delta t has in fact to be less than or equal not just 2 over pi times h, but 2 over c times pi times h. And this now actually makes sense from a, let's say, physical units perspective. Delta t has units seconds, h has units meters, c has units meter over seconds, so both sides have units seconds now. So what we often do when we talk about hyperbolic equations, there's sort of a language associated with this. And we often introduce something that is called the Courant-Friedrichs-Lewy number. That is something that was actually coined already in the 1940s, so a very long time ago, before the advent of modern computers. So Courant-Friedrichs and Lewy in that paper in the 1940s defined a factor of the kind delta t times c over h. So that relates the time step and the mesh size and the wave speed. And what we have just found out is that this method is stable if this CFL number is less than 2 over pi. Like I said, every time-stepping method has a different factor, but typically what it means is that the CFL number must be less than or equal something. So the CFL number, again, relates the time-step size to the mesh size in their correct physical units. So the CFL number, that is something that you will hear very, very frequently. And a restriction is always CFL is less than 1 or less than a constant for a method to be stable. Now let us do the same thing again for implicit methods. So for implicit methods, I get that I need to evaluate this a times u term at times tn. If I bring everything with un over to the left, everything with un minus 1 and un minus 2 over to the right-hand side, I get an equation like this here. Okay, I do the same kind of expansion as I always do. I find that mu in k, so the kth expansion coefficient in our eigenvector basis at times tn is given by this whole thing here. Okay, and you see again that if I assume that these two expansion coefficients are the same, for example, for the previous two time steps, that I get an amplification factor here that is always less than 1, because I know that the eigenvalues are positive, and 1 over 1 plus something positive is always less than 1. So what we get immediately from this is that implicit time discretizations for the wave equation or for any second order hyperbolic problem are again unconditionally stable for any time step size. So you might think that I can choose the time step as large as I want. But that actually turns out to be not quite true. So for parabolic problems, I could do this because I expect that the solution becomes smoother and smoother and that I can use fewer and fewer time steps as time progresses. You have this sort of trade-off always that when you discretize things in time, that maybe you have some time step that is stable, but that isn't very accurate. And so for the hyperbolic equations like the wave equation, that is exactly the limiting factor, that you cannot expect to make the time step as large as possible, because while the method might be stable, it will not be accurate anymore, for exactly the same kind of reasons that I explained at the top of this lecture. So that is summarized again on this slide here. So because in For the wave equation, we transport information undamped at a speed c. We can argue that, for example, the time to transport information from one cell to the next cell, if you just think of the wave equation as something that translates a solution by a certain distance c per time step, okay, or per unit of time, then the distance you transport information per time step is going to be delta t times c. And you can reverse this and you can ask, how long does it take for information to be transported from one cell to the next cell? And that time is exactly h over c. Okay, so if I make my mesh size smaller and smaller, then the time to transport information from one cell to the next also becomes smaller and smaller. And the proportionality constant is 1 over c. So what you see from this is that the amount, or let's say that the time to transport information from one cell to the next is proportional to h over c. That for let's say intuitive reasons, I cannot expect to choose a time step that is much bigger than h over c. And I summarize this here in the following way. So if you look at this, the, let's say, ith component of un is given by the ith component of un minus 1 of this one here. This is a diagonal matrix. This A actually just is, in the 1D case, it's a tridiagonal matrix. So it couples every cell with its neighbor cells, for example. And so every, the ith, let's say the value at the ith node of my finite element mesh at time tn, because this A is a matrix that only couples neighbors, only depends on the immediate neighbors. Okay, so if you think, for example, no matter how large I make that time step, the solution at every given time step will only affect the solution at the neighbor nodes at the next time step, no matter how large the time step is. And that, of course, does not match the physical intuition that we have, because there the influence does depend on the amount of time that has passed. So I cannot expect to take time steps that are much larger than h over c just for accuracy reasons. I will get something that is stable but entirely wrong. On the other hand, for explicit time-stepping methods, I remember that the stability limit was something that's proportional to h over c as well. It was a factor that is not very far away from the one that I have here. So the accuracy limit that delta t must be less than h over c, and the stability limit that delta t must be less than or equal some constant times h over c, they actually match. They actually agree. For implicit time-stepping methods, I had no such restrictions. I had no stability limit. But if you think about what actually happens here, so you have, now you need to invert this sort of matrix, m plus delta t squared a in every time step. So this ith component of the solution vector does depend on all of the other components of the solution vectors at times un minus 1 and un minus 2, because the inverse of this matrix here is typically a full matrix. However, if you look at this matrix a little bit more closely, what you will find is that the matrix may be full. So m plus delta t squared a to the minus 1 is a full matrix, but in reality it does not couple a cell here very strongly to a cell that is far away. So in essence, that matrix has a very strong local dependence as well. And so for accuracy reason, again, we cannot expect that we can choose the time step much larger than h over c, even though we could for stability reasons. So the summary of all of this is that the time step limit for explicit methods is not unreasonable, and they're cheap. For implicit methods, there is no restriction on the time step, but for accuracy reason we have to choose it not much dissimilar from explicit methods. On the other hand, of course, implicit methods are expensive because I have to solve a linear system in every time step. And so the consequence of all of this is that for hyperbolic problems, one almost always chooses explicit methods for efficiency, because I could not choose a time step much larger if I chose an implicit method, but I have to do work that equals a large multiple of the amount of work that I have to do for explicit methods. And so as a consequence, the trade-off is entirely different for hyperbolic problems of second order than it is for parabolic problems. So parabolic problems, you always choose implicit methods. For hyperbolic problems, you always use explicit methods. And with this, I would say I'll finish the overview of these two, of the parabolic and hyperbolic problems of second order. And we'll look at one of the programs that implements this at a later time. And I'll move on then instead to transport problems in conservation laws. But that's for the next lectures.